Welcome back to Python tutorial 5 of the course Time Dependent Quantum Chemistry. So far we have seen how to propagate a wave packet in the zero interaction potential, when the particle is not experiencing at all the interaction potential, which means the particle is not experiencing the force acting on it. So we have seen that the particle is traveling with a constant velocity, and also we have seen that the particle distribution, the distribution function is spreading out slowly. So now the next problem we will deal with is the linear interaction potential. What will happen to the particle? What is linear interaction potential? It's a simple interaction potential you can think about. In the x space, you have Vx interaction potential to be like this. We have created this slope like this way because then it's starting from here and how it's moving. Clearly, because the slope is given to be minus b, b is a constant, positive constant, it should accelerate slowly. And classically it is also true, because if a ball is sliding over this slope, it will be accelerating, so it will be increasing the velocity as a function of time, and we will see what is going on. So linear potential can be a model for let's say I have a potential like this. This was ground state and this is excited state, and I have created a wave packet here, let's say, and for a short region of the potential it can be considered to be linear as a function of time, as a function of space. So linear potential can be considered to be a dissociative potential, one can in a simple form. And to understand the linear potential, remember, linear potential problem can be analytically solved using the technique which we have discussed in the translational motion of quantum particle, and we'll see whether we can represent the same thing numerically. And the difference between the linear potential problem and the interaction zero interaction potential problem is that now we have to consider the V. So previously what we have used here, this split operator approach, we have we didn't have any potential part. Now we have the potential part and we have to consider that potential part. And we can one more time write down that equation, that split operator equation, which is psi xt is going to be n products, n number of products of this short time propagator, which is nothing but I then t by 2 in atomic unit we are considering. So h cut is going to be 1, then delta t multiplied by e to the power minus I v potential delta t, and then e to the power minus I t by 2 delta t. This is the product we have, and then psi x0. So this is what we have to implement, and we know that this product has to be implemented through a for loop that is exactly here for I in range nt. Instead of range we are going to use a range functionality. So a range functionality will give me, and total number of time steps I can consider to be 60 or 100 depending on whatever we want. We want to keep it 100 because then we can compare with the 100 at the 100 atomic unit of time what happened. So what happens to that wave packet for the same time evolution. We can compare it to the free particle evolution, and we can see that this time when we are doing it, initially we have to PSI norm has been converted to its momentum domain. Then once we have the momentum domain function, that momentum domain function we are carrying out this kinetic energy part, the first kinetic energy part of the operator, split operator here in the momentum domain, and that is nothing but kinetic energy, that is the T multiplied with half 1 by 2, delta T is dt, and the I is represented by 1j. That is the representation in the Python programming. And after doing that, we have to convert it to position domain, because the next to this first part of the kinetic energy, next to this we have this potential energy, and potential energy part of the time evolution operator needs to be carried out in the position space. So that's why you have again converted to inverse Fourier transform and then get the position space part. Once we get the position space of wave function, we employ this position the potential part, the potential part of the split operator, split operator, and then again we have to carry out this kinetic energy part. So we have to again FFT, the fast Fourier transform we have done to get the wave function in the Fourier domain, and then employed the last part, kinetic part of the split operator, and then finally we get this PSI norm. This PSI norm will be updated during this iteration. So this iteration will be continued until this value or 100 minus 1 value, and it will be updated. Finally, I get the probability density, then we'll calculate the average values of this and variance, which is the full width, the half width at the 60%, almost 60% of the maximum, and then we are going to print it. And also we can plot the final probability to check how the final probability looks like. So that's the basic idea. Remaining part remains to be the same what we have done. Another thing is that we are now defining the potential here. So this was not present in the zero potential problem or zero interaction potential problem. Here we are defining the potential to be minus 1x. So the slope is going to be minus 1. So with this idea, we will now implement the entire program in our in Python, and here because we are going to plot it again, so we are going to use this from I can plot it later. So we'll keep all these things. Remaining part is the same. So creating and normalizing the wave function, and then what we'll do here is that we will first define the potential. So defining the normalizing the initial wave packet, we have done it, and then before the time propagation we will now define the potential. Potential definition V equals minus x. X is an array, so V will be getting an array, and array values is just multiply each element by minus 1, multiply the element of X array, and then we'll look at the time propagation part. When we look at the time propagation part, definitely we have to first create the K grid that we have created here. This is the K grid preparation. We have created the K grid. Then kinetic energy has been defined. For each grid point of K, we get the kinetic energy, corresponding kinetic energy, and then NT we keep it 100 and dt to be the same. So we'll be able to compare what is going on if it is a free particle. And then for we'll start the iteration for loop to implement the short time propagator, and for that what we'll do is that we will start t equals I plus 1 multiplied by dt. So T I am defining as I plus 1 multiplied by dt. Now this T definition, in many occasions we might want to check what is at what time I have this wave packet. I may not need it immediately, we will see later. So what we will do is that the remaining part is the same. FFT of the wave function, first we have to do FFT of the wave function, and then after FFT we will say time evolution due to first kinetic energy part of the propagator. And for that first kinetic energy of the propagator, it will give me psi norm, then k kinetic energy, we call it 1, and that has to be given by exponential of, so the name we have given the name to be exponential of minus 1 j kinetic energy dt divided by, now I have to divide by 2.0 and psi norm k. Then I have to do the first Fourier inverse Fourier transform of the real space, that is going to be k1. Then we have to employ time evolution due to the potential part of the propagator, and this will name it psi norm. This we name it as the 1. So the kinetic energy is done, then potential energy, that is going to be psi norm one. So this is the potential energy part. Now this is not potential energy, we have to define the potential, Ij multiplied by V multiplied by dt, there is no half. So this is the potential part we are doing. After doing the potential part, I have to now again Fourier transform to k space, and for that this is the function which I will Fourier transform, and I give the name to be k. This is the Fourier transform. After Fourier transforming, again I have to time evolve it, and for that we have to employ the kinetic energy part again, but this is the second kinetic energy part we will be carrying out. And now I have, this is the function, and I will name it two. Then we have to inverse Fourier transform to the real space. To the real space. Here I am going to now update this psi norm, and this is the function which I have here. So this time I'm going to update this so that this PSI norm will be used in the next iteration in this place. So then I can bring the probability density to be, the final probability density is going to be PSI norm. There's the same thing we keep. Then average values we're going to calculate. Average one is going to be Simpson's method of numerical integration we are using. That is the final multiplied by x, and then average 2 is going to be final multiplied by x, and then variance is the same thing, and print, we're going to print the width as variance and the expectation value of the average one. So this is what we are going to do. So if we do that, if we run the program, then we see that the width we have found to be 7.10 for this step, nt equals 100. But if we make it, let's say nt to be 2, then the center position is now 0.22 atomic unit. Previously it was 60 atomic unit for the 100 steps, but here we have taken 2, so it's going to be 0.22. And this is the way, if we keep collecting all the values, possible values, we'll go back to the slide now, and if we keep collecting it, we'll be able to get it. But if we plot it, what we see here is that we started with the same initial Gaussian wave function, which is centered at x equals 0. This is x atomic unit, and it is centered at x equals 0. This is at t equals 0, and we have considered nt to be 100 here. So we see that nt to be 100, we can this is centered almost at 25 atomic unit, whereas the free particle we have found it was centered at 10 atomic unit. This was at 10 atomic unit, which shows that because of this slope in the potential, it is moving much faster, and it is moving much faster. And if we keep collecting the values at different time, we'll see that initially if we plot it, this one, then what we can see here is that this is the average or variance plot as a function of time. This is function of time, average or the variance plot. So this is variance and this is average plot. What we see is that now there is a striking difference between the linear potential particle experiencing linear potential, and the particle experiencing zero interaction potential. This is V equals 0, this is the potential, and V equals minus x, that's the potential it's experiencing. What we see that the mean position is non-linear with respect to time, and that should be because if x is non-linear with respect to time, some kind of, let's say, t square, for an example, I don't know, I have to check the non-linearity, I have to feed this data with certain function, but if we assume that it is x equals t square, then only I get dx dt to be time dependent, which means velocity is time dependent and velocity is changing as a function of time, and that should happen. Classically also it should happen. If I have a ball sliding through this slope, it's slowly accelerating, which means that velocity depends on time. Similarly, if a wave packet is created here, when the wave packet will be propagating in space, it will be accelerating its velocity. Its velocity is increasing, and that's why the mean position or center of the velocity, center of the wave packet is nonlinear now with respect to time. And sigma also, we have seen that sigma is also kind of nonlinear, is nonlinear, but it is also spreading out. So both the one similarity between the zero interaction potential and the linear potential problem is that both are spreading out. Here the width and here the width are different. Both are spreading out, but in zero interaction potential its velocity was constant, but in the particle which is experiencing a linear potential of this kind, minus x kind of potential, if it is plus x kind of potential the situation can be different, but if it is minus x kind of potential it is accelerating, and that is quite expected. And it is because accelerating, it is the mean position is slowly it's nonlinear with respect to time. So this entire procedure, particularly what we have given here, this entire procedure is now can help anybody to express the Wavepacket dynamics following the symmetrized split operator approach. In order to implement this split operator approach, all we need to know is that potential. What is the potential experienced by the particle? As long as the potential is known by the user or by somebody who is exploring this dynamics, one-dimensional dynamics, and as long as the initial wave function is known, this is the initial wave function, traveling Gaussian, this initial wave function is known, then one can time evolve the particle on that potential. One of the simple problem can be, one can think of a dissociative potential like this, and one can create the wave packet here and check what is the dynamics of the wave packet on this kind of dissociative potential. And now this kind of dissociative potential can be found or can be calculated with the ab initio calculations. One can use Gaussian calculations, small pro calculations, and find out the potential, and that potential can be used to check the how the particle is actually moving on that kind of potential, and that's representing the dissociation of a chemical bond. So we have almost come to the we have come to the end of this present tutorial, Python tutorial. What we have seen is that we have numerically solved or numerically time evolved the wave packet starting from the Gaussian wave packet as an initial Gaussian wave packet. We have used this technique, we have implemented this split operator approach in Python programming for zero interaction potential and linear potential. And we have seen how to plot the mean position and the width of the wave packet as a function of time. This procedure is general procedure. One can use it for any unknown potential, but it has to be one-dimensional in nature. That's the way we have studied so far. Multidimensional Wavepacket dynamics is a little more complicated. If time permits, we'll definitely think about it and we'll present it. So we'll stop here. We'll meet again for the next module.